You measure the position of an electron. Perfect. You know exactly where it is. But now, try to measure how fast it's moving. Which direction? You can't. Not because your instruments are bad, not because you disturbed it, because nature herself won't let you. This is the uncertainty principle, and it's not a limitation of measurement, it's a limitation of reality itself. Let me be very clear about what this is not. It's not like trying to measure the speed of a car while it drives past you, where if you had better cameras, better timing devices, you could get both the position and the velocity perfectly. No, the uncertainty principle says that an electron simply does not have both a definite position and a definite momentum at the same time. Not that we don't know them, they don't exist together. Period. Now, this sounds completely absurd, doesn't it? How can something not have a position and a momentum simultaneously? Everything you've ever seen has a position and moves with some velocity. But electrons, protons, all quantum objects, they're not like tennis balls or planets. They don't follow the same rules. And here's where it gets interesting. Let's think about waves for a moment. Imagine a pure sine wave, one perfect wavelength, extending forever in both directions. What's the wavelength of this wave? Easy. You can measure it. It's completely defined, one value. But now, where is this wave? Where is it located? Well, it's everywhere. It extends to infinity. There's no particular location you can point to and say, the wave is here. The wave has a perfectly defined wavelength, but a completely undefined position. Now flip it around. Imagine a wave that's completely localized. A sharp pulse, just one spike. Here, this location. Where is this pulse? Perfectly defined. You know exactly where it is. But what's its wavelength? Well, it doesn't have one. A single pulse isn't a repeating pattern. There's no wavelength to measure. You've localized the position perfectly, but you've lost all information about wavelength. And here's the connection. For quantum objects, momentum is directly related to wavelength. De Broglie showed us this. The momentum of any quantum particle is Planck's constant divided by its wavelength. P equals h over lambda. So if you know the wavelength perfectly, you know the momentum perfectly. But then the wave extends everywhere, and you have no idea about position. If you localize the position, you destroy the wavelength, and momentum becomes undefined. This isn't philosophy. This is mathematics. The wave function of an electron described by Schrödinger's equation has this property built into it. You cannot construct a wave function that has both a definite position and a definite wavelength. It's mathematically impossible. Nature simply doesn't allow it. But wait, let me be very clear about what this wave function actually is. Because there's a huge misconception here. When we draw a wave function, when we show these peaks and valleys, people think the electron is a wave, that it's physically wiggling up and down like a water wave or a sound wave. No, the electron is not a wave. It's a quantum object that possesses wave-like properties. Big difference. The wave function is not a physical thing moving through space. It's a mathematical tool, a function, psi of x, and what it tells you is probability. Here's what the axes mean. The horizontal axis, that's position, real physical space, x, y, z coordinates. But the vertical axis, that's not physical height. It's the amplitude of the wave function, psi. And here's the key. SI itself doesn't mean anything physical. You can't measure psi. What you can measure is SI squared. The probability density. If you square the amplitude at some location, That tells you the probability of finding the electron at that location if you were to measure it. High amplitude, high probability of detection there. Zero amplitude, zero chance of finding it there. The electron doesn't exist at that position as a wave. The wave function is describing where the electron could be found. It's a map of probabilities, not a map of physical undulation. This is subtle, but crucial. The electron comes in lumps, always detected as a particle at one location. But before measurement, before you look, the wave function spreads out, and its square tells you all possible locations where that lump could appear, and with what probability. That's what the wave function is. Now, let's get quantitative. The uncertainty principle says that the uncertainty in position, delta x, times the uncertainty in momentum, delta p, must be greater than or equal to h bar over 2. That's Planck's constant divided by 4pi. This is the fundamental limit. You can make delta x smaller if you want, but delta p will grow. You can make delta p smaller, but delta x will grow. Their product cannot go below this minimum value. And this number, h bar, it's tiny, about 10 to the minus 34 joule seconds, which is why you don't notice this in everyday life. For a tennis ball, the uncertainty is so small compared to the ball's size and momentum that it's completely negligible. But for an electron, the electron's momentum and size are so small that the uncertainty becomes everything. It dominates the behavior. Here's something remarkable. Think about the hydrogen atom. One proton, one electron. Classically, this shouldn't be stable. The electron is a charged particle orbiting another charged particle. Charged particles that accelerate radiate energy. The electron should spiral into the nucleus in a fraction of a second. But it doesn't. Why not? The uncertainty principle. If the electron tried to get too close to the nucleus, its position uncertainty would become very small, which means its momentum uncertainty would become very large, which means it could have enormous momentum, enormous kinetic energy, enough to blast it back out. The electron can't sit still at the nucleus because sitting still would mean both zero momentum and a definite position. Not allowed. So the atom stays stable. The uncertainty principle saves all of chemistry, all of biology, all of you. And there's something deeper here. The uncertainty principle isn't just about position and momentum. There's another version, energy and time. The uncertainty in energy, delta E, times the uncertainty in time, delta T, is also greater than or equal to h bar over 2. This has strange consequences. It means that for very short time intervals, energy conservation can be violated. Particles can borrow energy from nowhere as long as they pay it back quickly enough. This is how virtual particles work. They pop into existence, violate energy conservation for a brief moment allowed by the uncertainty principle, then disappear. And these virtual particles, these fleeting violations of energy conservation, they're real. They create measurable forces, the Casimir effect. Hawking radiation at black hole horizons. But that's for some other day. Let me address a common misconception. People say the uncertainty principle is about measurement disturbance. That when you measure position, you disturb momentum, like shining light on an electron to see where it is, and the photon kicks it. No, that's not it. Even if you never measure the electron, even if it's completely isolated, it still doesn't have a definite position and momentum simultaneously. The uncertainty isn't in our knowledge. It's in reality. Another way to see this, Imagine trying to build a quantum state with both definite position and momentum. Start with a wave that has one specific wavelength. That's definite momentum, but it extends everywhere. Now add another wave with a slightly different wavelength. They'll interfere. In some places they add up, in other places they cancel. You've created regions of higher and lower probability. You've started to localize the particle. But now the particle doesn't have one wavelength anymore. It has two possible momenta. Add more waves with different wavelengths. You localize it further. But each wave you add is another possible momentum value. The more localized the position, the more spread out the possible momentum values. It's built into the structure of waves themselves. And here's the beautiful thing. You can actually see this. If you send electrons through a single slit, you're constraining their position. The narrower the slit, the more precisely you know where they pass through. But look at where they hit the screen on the other side. The narrower the slit, the wider the diffraction pattern. You've decreased position uncertainty, so momentum uncertainty increased and the electrons spread out in different directions. It's not that we disturb them by measuring. It's that localizing them in space inherently means they have a spread in momentum. Now, there's something Bohr said that I think is important. The uncertainty principle isn't a sign that quantum mechanics is incomplete. It's not a failure of the theory. It's a feature of nature. Position and momentum are what we call complementary variables. You can know one or you can know the other, but not both. And this complementarity shows up everywhere in quantum mechanics. Wave-like behavior and particle-like behavior are complementary. You can design an experiment to see one or the other, but never both simultaneously. Some people find this disturbing. Einstein certainly did. He didn't like the idea that nature is fundamentally probabilistic, that there are limits to what can be known. He thought there must be hidden variables underneath, deterministic things we just haven't discovered yet. But experiments, Bell's theorem, they ruled this out. The uncertainty isn't because we're missing information. It's because that information doesn't exist. But that's for some other day. Let me give you one more way to think about it. In classical physics, you can specify the state of a particle by giving its position and momentum. 6 numbers in 3 dimensions. 3 for position, 3 for momentum. That's the phase space. But in quantum mechanics, you can't do that. The best you can do is specify a region in phase space with an area of at least h bar. That's the minimum cell size. You can't say the particle is at this point with this momentum. You can only say it's somewhere in this fuzzy region. And the fuzzier you make position, the sharper momentum becomes, and vice versa. This has profound implications. It means that even at absolute zero, even when you've removed all thermal energy, particles still have motion. 0-point energy. The ground state of a quantum system isn't a state of rest. It's the state where the uncertainty is at its minimum value. The particle is still jiggling, still fluctuating, because to be completely at rest would violate the uncertainty principle. Now, I want to emphasize something. We can calculate all of this precisely. The uncertainty principle isn't vague. It's not hand-waving. It comes directly from the mathematics of wave functions and Fourier transforms. If you know the math, you can derive the exact numerical bound. H bar over 2, not approximately. Exactly, and experiments confirm this to extraordinary precision. But here's what we can't do. We can't visualize it in terms of everyday experience. We evolved to understand objects at human scales, objects that have definite positions and move with definite velocities. Our brains didn't evolve to understand quantum mechanics. So when you try to picture an electron with an undefined position, or think about how it can be in multiple places at once, your intuition fails. That's not a failure of the physics. It's a limitation of evolved human cognition. What we can do is follow the mathematics, calculate what the theory predicts, compare with experiment. And when they agree to 10, 12 decimal places, we know we're on the right track, even if we can't picture it. So let me bring this back to where we started. The uncertainty principle. It's not about measurement. It's not about disturbance. It's about the fundamental nature of quantum objects. They don't have classical properties like definite position and definite momentum simultaneously. They have wave properties, and waves, by their very nature, can't be perfectly localized in both position and wavelength at the same time. This is how nature works at the smallest scales, and it's responsible for the stability of atoms, the structure of matter, the colors you see, the fact that electrons don't collapse into the nucleus. It's not a bug in the universe. It's a fundamental feature, and once you accept that, once you stop trying to force quantum mechanics into classical pictures, it starts to make sense. Not intuitive sense, perhaps, but mathematical sense, experimental sense, the sense that comes from nature telling you how she works and you listening. That's the uncertainty principle. That's what it means. And that's why it matters.